Okay, in this video we're going to see what does work do? What is its purpose? So on our MCAS equation sheet we have a formula that says work equals delta E. Basically what this means is work can change the energy of an object. Now there's lots of types of energy of an object. An object can have kinetic energy, so sometimes that change in energy could be a change in kinetic energy. Sometimes it could be a change in potential energy or some combination. So these are the common forms of energy we're interested in. But sometimes that energy gets wasted. Sometimes it turns into heat from friction. And so really, these are the three options for work. It can be made into kinetic energy, potential energy, or heat. And we just got to account for which it is. So in this case, I have an object on the ground. It is 5 kilograms. And I am pushing it. Well, it doesn't say how long I'm pushing it for. All it says is I do 40 joules of work on it. So that's the work I put in. How did I do that? Did I do 8 newtons for 5 meters? Did I do 40 newtons for 1 meter? It doesn't matter. This is how much work was done. So in other words, this is how much the energy of the box has changed. So the box is still on the ground. It hasn't been elevated at all. So it has not gained any potential energy. So we could say the change in potential energy then is 0, has not changed. And it was moving, it was at rest, and now it's moving at 2. So the kinetic energy here was 0. So what's the kinetic energy over here? 1/2 mv squared. So 1/2 times 5 times v squared. So we can calculate that, and that comes out to 10. So the change in kinetic energy was 10. And so I put 40 joules in. I got 0 potential, 10 kinetic. All of it has to be accounted for, so the rest of it must have been wasted as heat along the ground. And so that's it. So it's all been accounted for. So all the work you put into an object should fall into one of these buckets, and they should add up. So let's look at another one. So here I have a ramp, and the ramp is 2 meters tall, and it's 8 meters long. So along this thing is 8 meters. And I have an object at the bottom, 6 kilograms. And it says that I push it with a force of 25 newtons all the way up this ramp. So 25 newtons all the way up this ramp. So the work I'm doing, work again is force times distance. So I push with 25 newtons for a distance of 8 meters. So I have done 200 joules of work on the box, moving it from here up to here. And now where did that work go? So again, work is change in energy. And so it can be a change in potential, it can be a change in kinetic, or it can be lost as heat. So let's start with potential. The box was on the ground, and it went up by a height of 2 meters. So it doesn't matter that it was at an angle. All that matters is it's now 2 meters higher than it was before. It started at 0, so the change in energy will just be the new total energy, or MGH. So if I do MGH, 6 times 10 times 2, my change in potential energy is 120 because it started with 0. It says that it now has a velocity of 2 at the top of the ramp. So it had a velocity of 0 when it started, and now it's moving 2. And so since it had 0 kinetic energy to start, the change will just be the new kinetic energy, 1/2 mv squared. So 1/2 times 6 times 2 squared. I get 2 squared is 4 times 6 is 24, it's 12. So my energy, I have 120 for potential and 12 for kinetic. Again, I put 200 in, so how much was lost to heat? They all have to add up to 200. So if I take 200 and I subtract these two numbers, this 132, then I believe I will get 68 joules of heat because these three all add up to 200. So again, everything you put in has to go somewhere into one of these three categories, and they should all match up. And so that's it. That's how I figure out how much is lost to friction. All the work you do changes the energy in some fashion. And if it doesn't change the mechanical energy, it gets wasted. It makes heat through friction. So that's it. So until next time, I am Derek Genova. Have a delightful day.